Can everybody see my screen that has the question number 1 on it? All right, great. So does anybody have an answer for this one? I'm going to assume that a lot of people do. We're looking for the best reagents to make this compound. Just 2-pentine. Or sorry, 2-hexine rather. Yeah, I think it's A as well. Right? I think it's A. If you take a look, you look at A, we've got a good nucleophile. This is an alkanide, and that would do a nucleophilic attack on propyl bromide. And I can't draw the loss of leaving group without being ridiculous because we don't have the bond drawn there. But if we look at the number of carbons, we have a total of what? 1, 2, 3, 4, 5, 6 carbons. If we were to do B, the problem here is that you only have 1, 2, 3, 4, 5 carbons, so that's not enough. Here you have 1, 2, 3, 4, 5, 6, 7, so that's too many. And indeed, there's no nucleophile and no electrophile. Okay, so no reactivity. So this is A is going to work just fine. It's just a regular old SN2 reaction. You have a good nucleophile. You have a primary alkyl halide. You just do an SN2 reaction. There you go. So the answer is A. Everybody got that one 100% correct. Let's move on to question number 6. So question number 6, it says, what would be the major product of the dehydrohalogenation of 3-chloropentane by potassium hydroxide? So let's draw what 3-chloropentane is. So if we draw 1, 2, 3, 4, 5, oops, let me draw it a little neater. 1, 2, 3, 4, 5. So if we had 3-chloropentane, there's no stereocenter in the molecule. If we were to treat that with potassium hydroxide, said what would be the major product? So we have a strong base. We've got a secondary alkyl halide. We're going to get mostly elimination. And here's our alpha carbon. We've got 2 beta carbons. Okay, we have a beta carbon here and a beta carbon here, but those 2 beta carbons are identical. And so there's only one kind of beta proton in the molecule, and that would be this one right here. So that means we're going to get an elimination reaction, right? Because we've got potassium hydroxide, and so this is just going to do proton transfer and loss of leaving group, which is going to give us this compound, which is 2-butene. Now I've drawn it as trans 2-butene, but you see that none of the, oops, let me draw it a little neater. You see that none of the products are drawn as cis or trans, so it doesn't matter whether it's cis or trans. That's neither here nor there. We end up with 2, where's my pen? 2-pentene. Okay? We can see that A is not a possibility and B is not a possibility because they both have methyl groups on them, so I don't know where that would come from. If we look at C, C is 1-pentene, so that's not right either. But D is 2-pentene. And so that is our answer right there, nothing more than that. So it's just a straightforward E2 reaction. This is just a plain old run-of-the-mill, everyday E2 reaction. Nothing more to it. And again, the trans would be the major, since this one would only be stereoselective, not stereospecific, but either way, it doesn't matter. We don't have to know anything about that to answer the question. Let's move on to question number 9. And we went over this in quite a bit of detail in chapter, I can't remember if it's chapter 6. Anyhow, where we talk about cyclohexane. We spend a lot of time talking about cyclohexane and learning how to draw a chair, right? So we spend a lot of time practicing drawing a chair. And if we were to draw this molecule, let's say we call this carbon number 1 and we'll call this carbon number 2. So our bromine is pointing up like this. We have the hydrogen coming down. On carbon number 2, we have the methyl group going down like this. So this is our CH3 group here. And then we have the hydrogen going up. It's going to be up in equatorial like this. Now it says we've got a secondary alkyl halide, okay? and we've got a strong base. And so this is going to be another elimination. And it even tells us that, right? It's a dehydrohalogenation, okay? Now, if this is my alpha carbon, okay, I've got a beta carbon here, and I have a beta carbon here. And the two beta carbons are not the same because the one that's in blue has a methyl group on it, and the one in green doesn't have a methyl group on it. So could anybody tell me from which one of these carbons would the elimination occur? Would I eliminate the proton from the blue carbon or from the green carbon when I do my elimination reaction? It's going to be from the green one. Can anybody tell me why? It's because the green proton has to be, it's not about hindered and it's not about stability. It's got to be anti-coplanar, right? This hydrogen, oops, this hydrogen that I have in green and this bromine, they have to be anti-coplanar. So in order for the elimination, I need to be anti-coplanar. And this bromine can never be anti-coplanar to that hydrogen that I have in the red circle. And so the only product that you could form would be this, where you have your six-membered ring and your double bond is going to be here, and your methyl group is going to be pointing down like that, which is the same thing as just having, you know, a six-membered ring, okay, with a double bond and a methyl group like this. And so the answer is that we're going to end up with, you can't really see that very well, but the answer is that you're going to end up with A only, okay? You're never going to abstract a proton to put a double bond here, which would form this compound. This compound is impossible. So it might be a knee-jerk reaction to say, well, I'll pull off either beta proton and I'll get both of these. You can get this one, but you cannot get this one, okay? There you go. Can't get this, can't get this, and you can't get this. So there you go. The answer is A only. So remember, the requirement is that the leaving group and the proton that's being removed and the dehydrohalogenation on an aromatic ring, or even in a Newman projection, they have to be anti-coplanar to one another. All right, let's take a look at a question that involves a mechanism. And this is question number 16. It deals with dehydration. In fact, this is one of my favorite reactions. I mention it every time it comes up, where you just take an alcohol and you treat it with a strong acid and you do an elimination. And you know it's an elimination because it tells you that you're forming an alkene, right? So this is just a straightforward elimination reaction. Now we've got a secondary alcohol and we've got a strong acid. So I'm going to draw the bond line structure of the starting material, which would be this. We've got 1, 2, 3, 4, 5. So we've got 1, 2, 3, 4, 5. Here we've got our hydroxyl. Here's our hydroxyl, and then we have the two methyl groups over here. So this is our starting material. Now the first thing is going to be a proton transfer, right? Because we're in a strong acid. So I'm just going to draw a proton transfer. And if you want to draw hydronium out in all of its glorious detail, you could do that and draw the proton transfer. I'm going to make it simple because I'm just at the end of the class here and we're just trying to get the right answers to these multiple choice problems. So I would do a proton transfer like that. Okay. Now that's going to convert the hydroxyl into a good leaving group. So I'm going to delete that arrow. I'm going to delete this and I'm going to draw it as a good leaving group. So now that's a good leaving group. That's going to leave. Okay, so I'm kind of skipping the first step, the proton transfer. That's going to give me this carbocation. Let's draw it out. Okay, now what's going to happen to that carbocation? Can anybody tell me what that carbocation is going to do before we eliminate a proton? It's going to do a rearrangement, isn't it? Why? Because this is a secondary carbocation, but it can undergo a methyl shift to give us a tertiary carbocation, can't it? So that's going to rearrange to produce this. Now I know I don't have a lot of room here, so just bear with me a little bit. So now we're going to end up with this carbocation. Okay, and now we have a beta proton, which is going to be abstracted to give us the most stable alkene. Because remember, whenever you do this reaction, you always form the most substituted alkene, but you have to remember that if carbocation rearrangements can occur, they do, don't they? Right, so this is our rearrangement, and now we're going to rip off that beta proton. Right, the water is going to come in as a conjugate base, right, and that's going to just remove this proton and make the double bond. So what do we end up with? Let's draw it. We have the two methyl groups, so come on, you, there we go. We've got our double bond, we've got a methyl group here and an ethyl group here. So which one of those is, one of these compounds? Well, let's see. It is B. Right, we have the two methyl groups right here. We have the next methyl group, and then we have the ethyl group, and there you go. So there's the right compound. So the answer is B. So this is one where I would think you would have to draw the mechanism of the elimination, and this is an E1 elimination. Right, we went over this mechanism in detail. So here's the answer. It's B, and this is an E1 with a carbocation rearrangement. So you have to know that that is going to occur. And so this would be a good candidate for using your scratch paper, I think, unless you're able to solve that in your mind, which is totally doable. But I think that most students would probably want to use a piece of scratch paper just to double check. All right, let's move on from there to question number 17. Next question. It just says, if you're doing a dehydration of cyclohexanol and sulfuric acid, right? If you're taking cyclohexanol, which is this compound, okay, and you're doing a dehydration in sulfuric acid. So you've got, sulfuric acid and water, which is going to produce hydronium. Eventually, after a few steps, you're going to dehydrate that to form cyclohexane, right? You're going to lose water. Well, it's asking us, what is the first step? Could anybody tell me what the first step would be? Which one of these would be the best answer? It's the first step in the mechanism. Exactly. It's D. It's the protonation of the alcohol to convert it into a good leaving group. So this is all it is. It's just the proton transfer to form this, right? So now you've gone from a poor leaving group, right? This is a poor leaving group, and now we have a good leaving group. And that's all it is. The first step is the proton transfer, and then this could, leave like that. All right, there you go. So that's all the first step is. It's just protonation of the alcohol to convert it into a good leaving group. I think most people would probably get that after practicing their mechanisms. Let's move on to question 20. And question 20, here it is. Oh boy. So this is exactly how exams like an MCAT, how those kind of exams like the MCAT or the DAT or the PCAT, they can test you on mechanisms, right? Without getting you to draw a mechanism. They can show you this kind of thing right here. It says, which one of the mechanistic steps shown is not a reasonable one in the mechanism to describe the formation of 2-methyl-1-butene, that's this compound here, by the dehydration of 3-methyl-2-butanol. So look, they're even taking this and they're converting it into a Hoffman alkene, which is something we wouldn't think of. But they're saying like maybe it's not the major product, but they're saying it is a possible mechanism, okay? Or a possible reaction. Is there anything here? I'm just going to throw it out there to you. Is there anything here that looks really messed up? That doesn't look like it would be part? I'll give you a few seconds to look at the possible answers. I'll give you a clue. There's one thing in here that's really doesn't look good to me. Really kind of messed up. So A looks okay to me because the first step would be the proton transfer, right? You would do the proton transfer to make a good leaving group, then that leaving group would leave to form a carbocation. So I would say that A is okay. So we would form this carbocation, and this carbocation can definitely rearrange. You see that this is a loss of leaving group. This is a carbocation rearrangement. You go from a secondary carbocation to a tertiary, so I say that's good too. D is the elimination, right? After you form this carbocation, D would actually be the last step in the mechanism, right? Because you'd have to take that tertiary carbocation and you have two types of beta protons, right? You've got these beta protons here and you've got these beta protons here. Now I know what your knee-jerk reaction is to pull off the proton in green to make the Zaitsev product, but they're showing a Hofmann product, right? So for that, you'd have to pull off the proton in blue, and so D is totally reasonable. Can anybody tell me what's jacked up about C? There's two problems with it. There's two problems with C. Remember, we're talking about making this specific compound. There's two problems with C. Let me tell you what they are. Number one, you've got a primary carbocation. Okay, carbocation. We have never seen a primary carbocation in this class. Okay, we didn't see it before, so we're not going to start on the final exam. Okay, that is very, very unstable. And also, it's asking you not about like, hey, what can happen, and what it's talking about the mechanism to describe the formation of that molecule. So we're talking about this specific molecule. In order to make that molecule, why in the hell would you make a carbocation out there? There's no reason for it. Okay, because then you're thinking, I know that the knee-jerk reaction for students is to say, well, I would try to make this compound. You know, I want to make if I had this, then I would end up with this compound, but that's not what we're trying to make, right? We're trying to make this compound. And so this has nothing to do with it. Whereas this proton transfer here does produce this compound. So this proton transfer is good. All right. So this is a rearrangement in C that would never occur. It's no point, no reason for that to occur. Does that make some sense? Give me a thumbs up if that makes some sense. If it doesn't, we can dive deeper a little bit. Okay, cool. Well, let's try another one that involves kind of an interesting carbocation rearrangement. This is one that I noticed a couple of semesters ago because I've done every problem in the study guide a couple of times. But this one is one that kind of piqued my interest. We didn't really cover this in our lecture, and I'm not going to start asking you new things on the exam, but I thought this was an interesting question and I wanted to share it with you because I don't see why this couldn't be fair game for a standardized exam, like an MCAT or those kinds of things. It says predict the major product of what's going on here. So you see that you've got this nice secondary alcohol and you're treating that with a strong acid. Well, what's going to be the major product? It's going to be, well, sorry, I'm not going to answer the question. The first thing that's going to happen is proton transfer, right? To convert that into a good leaving group. So let me show you. After you do the proton transfer, so let me put some lone pairs in here. You do the proton transfer like this, and let's draw what the intermediate looks like. So you end up with this. You got a methyl group here, then you've got a good leaving group on here. Okay, so check this out. If this leaving group leaves, okay, then what do you end up with? You end up with this. You've got your cyclobutane, and then you've got a secondary carbocation like this. So this is a secondary carbocation. And so what's interesting is that the secondary carbocation, you might think, well, there's no way to do a methyl shift or anything like that. Or you might think, well, couldn't I shift this open or shift this over like this, and then I'd end up with a tertiary carbocation? That is true. You could do that. However, you would still have a four-membered ring. And a rule in organic chemistry that's not discussed a ton in our class, it came up a little bit, is that whenever you can form a five-membered ring or a six-membered ring in organic chemistry, it's always preferred. And so what would happen here is that this sigma bond, you'd actually take those two electrons and put them in here like this. And what that causes is it causes a ring expansion. So now you go from having a four-membered ring to a five-membered ring. Okay, so if I count the carbons, if I go 1, 2, 3, 4, if I put my methyl group here and I have 1, 2, 3, 4, like this, then this carbon that has the carbocation, that would be carbon 5 right there. And now it still has the methyl group on it. Oops, I wanted to draw it in black. It still has the methyl group on it like that. But now the carbon number 1, since it lost those 2 electrons, now carbon number 1 has the positive charge. So that's your carbocation. Okay? And now that you've got the carbocation, bromide can come in as a nucleophile. So bromide can come in like this. Okay? And then you would end up with C. Anyhow, this is a rearrangement that involves a ring expansion. Again, I don't think I put this on your final exam, so don't be like stressing all about ring expansions, but it is kind of a cool problem, and I don't think it's intuitive, you know, unless you think about rearrangements or anything that can involve, you know, a 4-membered ring rearranging to give you a 5-membered ring will always be favored in organic chemistry. It's a recurring theme that you would see if you were to take, say, advanced organic chemistry or something like that. 5-membered rings and 6-membered rings are always preferred because they have such less strain, right? They don't have the same kind of ring strain as 3-membered rings and 4-membered rings do. Well, let's move on to question 31. 31 and 32. Okay. I'm going to give you a second. I want you to look at this question carefully. I'm going to try not to talk too much for a few seconds here because I want you to try this question yourself. It says, what represents the proper flow of electrons in this E2 elimination? So it's just a plain old E2 reaction. Remember that a tosylate, this thing here, that's a good leaving group. So you have a tosylate and you have, this is an ethyl group. So this is the same thing as sodium ethoxide, right? An ethyl group, CH3, CH2, is the same thing as C2H5. It's the only way to arrange the atoms. So we have sodium ethoxide, and we have a tosylate on carbon 2. So let's zoom out here so you can see. And if anybody can show me the proper flow of electrons to produce 2-butene, let me know. Does anybody have an idea about question 31? Okay, yeah. I think the best answer is A. Okay, if we look at A, you see that in an elimination, we have a proton transfer and we have a loss of leaving group, right? And what would that form? That would form this compound. It would form 2-butene. I drew it as trans, doesn't matter. You see that in B, we have some serious problems here, okay? This is a leaving group. You would never see a pair of electrons going from a leaving group to form a double bond, and a tail of an arrow always has to start on a pair of electrons or a bond. Here it's starting on an atom, which is totally jacked up, okay? So that's totally wrong. And then here you also have the head of an arrow ending up on a negative charge. I mean, that could never, nothing could be more wrong. So B is an impossibility. If we look at C, we have the negative charge and the tail of the arrow going on a nucleus, but that nucleus doesn't have a leaving group on it, right? So it would have to have a leaving group in order to draw this arrow, right? How could this proton just spontaneously take this pair of electrons and attack a carbon? That's impossible. So we're going to cross this one. I mean, this leaving group leaving isn't that bad, but the first two arrows are pretty jacked up. But if we look at D, we have the leaving group leaving to give us a carbocation, okay? But that would be an E1 mechanism, right? This is a first order mechanism, first order reaction, the way it's drawn, right? One step at a time. First, you have the loss of leaving group, then you have the proton transfer. And we know that since it is an E2 reaction, it is a concerted process, right? It is second order. So that means that the proton transfer and the loss of leaving group occur simultaneously. So the answer would be A. So remember, you got to know the rules for drawing curved arrows. You know what represents a proper curved arrow and what represents a crummy curved arrow. Let's move on. Let's try one more question in this section. And this is something else that we looked at in gross and dirty detail. I remember doing it very well. Is question 32. What's the major product of this reaction? You know it's going to be an elimination. Three of the products have double bonds. We have a tertiary alkyl halide, so it's not going to be a nucleophilic attack. No way at all. You have a strong base or an ethanol. We have a sawhorse drawn here. But what's the requirement? The requirement is that we have our leaving group. Here's our alpha carbon. Here's our beta carbon. We've got a proton that we can't abstract, okay? And we have a non-hindered base, so our major product is going to be the Zaitsev alkene, so it's going to be forming the double bond here. But the requirement is that the hydrogen that I have in the red circle and the bromine have to be anti-periplanar to each other, okay? So the problem with A is that it's a substitution, okay? That's not going to occur. The problem with B is that you ripped off this proton, okay? And this is a non-hindered base, so it's going to pull off the most hindered proton to give you the most stable alkene. So this one is a Hoffman alkene. And then if we look at C and D, they're both Zaitsev alkenes, aren't they? Right? What's the difference? Is that they're cis and trans. This one is trans and this one is cis. So we have to draw this out because this reaction is stereospecific. Stereospecific, right? Put another way, this is a chiral center and this is a chiral center. So now we have to draw the Newman projection in such a way that the bromine and the hydrogen are anti-periplanar to one another. All right. So you can do the Newman projection, like you can take your eyeball and look down the double bond this way and draw the Newman projection. That will totally work. That's the way that I showed you in class. If you just say, hey, you know what, Mr. Dion, all I'm going to do is I'm just going to rotate this over here, and then that would put the hydrogen. Let me show you. If you were to rotate this 120 degrees clockwise, let's say, then you still have your methyl group up here. You have your bromine over here. You have your phenyl over here. So this is C6H5, which is a phenyl. I showed you that earlier today. Then your proton would be here. Your phenyl would be over here, C6H5. And your methyl group would be down here. If you do that, and then you say, okay, Mr. Dion, now I've got it. These two groups are anti-periplanar to each other. Okay, I'm going to eliminate them, right? The potassium hydroxide is going to, let me draw it over here. The potassium hydroxide is going to rip off this proton, form the double bond, and I'm going to lose my leaving group. And when I do that, I see that my two methyl groups are on the opposite sides and that my two phenyl groups are on the opposite sides. And therefore, I'm going to end up with this compound. Okay, I'm going to end up with the E compound or the trans compound. That totally works if you want to do it that way. But let me show you, if you want to draw the Newman projection, and I'm going to go over it with you one more time. And this is something that we looked at several examples of. Okay, so I'm just going to try and redraw the sawhorse for you in a little more detail. So if you wanted to do it on scratch paper, you might want to try it this way. So we'll draw the methyl group. Again, this is question 32. We have our bromine coming over here. We have our phenyl down here. We have our hydrogen up here. And this is the way, again, that it's drawn in the question. And then we have a phenyl down here. And again, phenyl is the same thing as C6H5. Okay. So if we were to take this compound, the way that it's drawn, it's going to move it over here. And if you were to take your eyeball and look down this carbon-carbon axis, what do you see? Let's draw it. So we have the carbon in the front. We've got a methyl group sticking up. We've got a bromine coming down like this. We got the phenyl over here. The carbon in the back. We have the phenyl going down. We have the hydrogen over here. And we have the methyl group over here. So what I'm going to do is I'm just going to rotate this one. I'm going to rotate. The bromine's going to go up here, right? The phenyl group's going to go up here. And the methyl group's going to go down here. So let's draw what that would look like. I'll draw it over here. So everything in the back stays the same. I've got the hydrogen over here. I've got my methyl group over here. Phenyl coming down. But now I've got my bromine antiperiplanar to my hydrogen. I've got my phenyl up here. And I've got my methyl group down here like this. So now you see that the hydrogen and the bromine are antiperiplanar to each other. So that when I eliminate them, you can clearly see that if I draw this carbon in blue, okay, it's going to have a double bond to this carbon. We'll say that this one is red, maybe, okay? Draw that this carbon is in red, okay? So we'll put it like that. Okay, so on the carbon in blue, I've got a phenyl up here, a methyl down here, and on the carbon in red, I've got my methyl up here, and I've got my phenyl down here. And so this is a trans compound or an E compound. Either way works. Okay? Now if we go back to the study guide, way back here somewhere. Where's the problem we were looking at? Which one was it? 32, right? Yes, there we go. So that means that the answer is C. All right. And again, either way is totally fine. If you can solve it in your head even faster than I did it, more power to you, no problem. But remember, this is a stereo-specific reaction. And I remember we spent like probably a half an hour on that one day going over stereospecificity when you have two chiral centers. Remember, if there was two beta protons on here, right, let's say we're the methyl group, if that was a beta proton, then the reaction wouldn't be stereospecific, it would be stereoselective for whichever alkene is less sterically hindered. All right, and that brings us to the end of the section on nucleophilic substitution and elimination. So we're going to move over to the section on electrophilic additions. So we have to go to the second part of the study guide.